Today we're going to be taking TNOTES on 5.1, and this will be part 2 of Unit 5.1. We will be talking about electric current, conventional versus electrical or direct current, electron drift speed, potential difference, equipotentials, and EMF. Let's begin. So we talked about current being a movement of charge. We know that there are positive and negative charges and that these can move. However, an electric current focuses on the movement of electric charges as the carriers of the charge. Electric current is caused by electric fields that produce a potential difference, or volts. The electron source is the conducting material itself. It is measured in amperes, or amps, sometimes referred to as amps. And remember that 1 ampere is equivalent to 1 coulomb, which is the SI unit of charge, which is equivalent to 6.24 times 10 to the 18th electrons per second. Conventional current is known as the electric field direction within a circuit that is defined as the direction that positive test charges are pushed. Electrons move in the opposite direction due to traditional ideas. Let me go ahead and explain with this schematic diagram. We see a schematic diagram which is a representation of an electrical circuit. An electrical circuit is just a closed system that allows the flow of charge. Here we see a positive and a negative terminal, which is the source of the potential difference. For example, this is a circuit of a battery, which uses stored energy or chemical energy in the form of ions to create a potential difference, which then causes the electrons to flow. The ions in the battery cause the negative terminal to interact with the electrons at the negative portion of the conducting materials to move along to the positive terminal over on the other side. If this system is completely closed when the switch is connecting the circuit, then all of the electrons can then flow from one end into the next. Back in the day, Benjamin Franklin, he didn't know about protons and electrons. We had no idea what they were. What Franklin did believe and what we did know was that there was movement through electrical wires, and he called these things charges. He assumed that there was only one kind of charge, and that the charge moved from an area with an excess of charge to areas with less charge. He called the spots with an excess of charge positive, and the spot with the deficiency is negative. So, the positive area, located here, is an area with a high potential difference or voltage. A negative area would mean an area of low potential difference or low voltage. As a result, the direction of an electric current was established to be in the direction that positive charges would move away from the positive terminal and move towards the negative terminal of the battery. This is called the conventional current flow, and it moves from positive to negative, which is an area of high potential difference to low potential difference. Electrons, however, would actually move through the wires in the opposite direction, and they would go from the negative terminal to the positive side. So, the actual movement of the electrons is called the direct current, which is in the opposite direction of the conventional current flow. Although electrons would flow from negative to positive, by convention or agreement, physicists refer to conventional current as a flow from high to low potential. And this is correct, but the actual flow of electrons is from negative to positive. We simply honor Franklin's achievements by continuing with this idea. Also, because electricity and magnetism were set up on the assumption that charge carriers were positive, the rules would need changing, so it was just easier to keep things as they are. Current, denoted as the capital I, is defined as the total charge that moves past a point divided by the amount of time to a charge past that point. The equation shows that I equals delta Q, which is in coulombs, and that is the charge, the change in charge, divided by the change in time in seconds. So we get amperes, which is coulombs per second. Here is an example for you to try. Calculate the current in a wire through which a charge of 25 coulombs passes in 1500 seconds. Pause the video and start it back up when you're ready to check. Okay, so with this example, we're going to be using the current equation, and when we plug everything in, we get 25 coulombs divided by 1500 seconds, and we get a total of 17 milliamps. Electrons' movement is affected by electric fields. When electrons cover a certain amount of distance in a given amount of time, the electron is said to have a drift speed, and it is defined as the average speed that a particle attains due to an electric field. The equation that is located in your data booklet is I equals N capital A times V times Q, where I is the current in amperes, N is the number of charge carriers per unit volume, A is the cross-sectional area of the conducting material, V is the drift velocity of the charge carriers, and Q is the charge carried. If you solve for V, then we can actually solve for the drift speed, and that would look like V equals I divided by N times A times Q. Here is an example. A current of 3.0 amps flows through a copper wire of diameter 0.001 meters, which has 8.5 times 10 to the 28th free electrons per meters cubed. What is the drift velocity? Go ahead and try this and then start the video back up. We have all of our information here in order to figure out the drift velocity. The only problem is that we do need to figure out what the area, the cross-sectional area of the conductor is, and we are given the diameter. We know that the area of a cross-sectional portion of a circle is pi r squared. So the radius is half the diameter, so we take pi times 5 times 10 to the negative fourth meters is half of this 0.001 meter. And we square that. When we put everything in, we get an answer for the area as being 7.85 times 10 to the negative 7 meters squared. Then we use our drift speed equation and we plug everything in, and we should get an answer of 2.8 times 10 to the negative fourth meters per second. If there are two positive charges, as in this diagram here, as the positive charge moves from point A to B, the amount of force and work that is needed to move to location B will increase because this charge is positive and there is a natural repulsion between the two particles. Because it would take some amount of work to move the charge from point A to point B, we say that there is an electrical potential difference between A and B. To calculate this potential difference between A and B, we would need to know the charge that is being moved. For example, we know that the larger the mass, the more energy and force it would take to move the mass from A to B. Potential difference is defined as the measure of electrical potential energy transferred from an electron when it is moving between 2 points in a circuit. The unit of measurements is in volts. What this means is that the electrical energy is converted to another form of energy per unit of charge. For example, a 2-volt light bulb converts 2 joules of energy for every coulomb of charge that passes through it, and it changes it from electrical energy into some other kind of energy. Here are more examples to show you that potential difference is when the electrical energy transforms into other forms of energy. The toaster here transfers the energy from its electrons to produce thermal and light energy. A blow dryer takes electrical energy and transfers it into mechanical energy and thermal energy. Electrical energy results in the TV emitting sound and light, as well as thermal energy. The equation to calculate the potential difference is V equals W divided by Q, and W is the work, which is in joules, Q is the charge, which is in coulombs, and we know that potential difference is denoted as the letter V. Potential difference can also be defined as the work done per unit charge to move a small positive test charge between 2 points. All we did was take the equation that we saw on the last slide and we solved for W. So that is pretty much what work is defined as in regards to potential difference. What this says is when a charge Q is accelerated by a potential difference V, then the energy that is gained by the charge is equal to VQ. It's very important to remember this. The amount of energy needed to move an electron through a potential of 1 volt is called an electron volt. This equation is shown here, W equaling V times Q. This equation simply states that the work is done when the charge moves through a potential. When we multiply 1 volt times the charge of an electron, so this is 1.6 times 10 to the negative 19 coulombs, we get 1.6 times 10 to the negative 19 joules. If we know that W equals VQ, then we also know that W equals EV, and this is the charge. So we can then connect this with the kinetic energy being 1/2 mv squared. Therefore, we get this equation here, which is EV equals 1/2 mv squared. Electric motive force, also known as EMF, is not a force. Electromagnetic force is known as the total energy that is converted to electrical energy per unit charge around the circuit. This is when the energy is transferred to the electrons, thereby transferring a form of energy to electrical energy. And it is measured in volts. So let's take a look at this example. An example here is with a battery. Inside the battery cell, there are chemicals, and those chemicals inside the cell get converted into electrical energy. Here we have a 9-volt battery that is converting 9 joules of chemical energy into electrical energy. So across the terminals of the battery would be an EMF. Another example is with a solar cell. A solar water heating unit shows how EM energy is transferred to the electrons and forms electrical energy. The voltage that is being produced by the solar cell must be an EMF because it is taking the light energy and it's transforming it into electrical energy, thereby producing a voltage. The next part that I want to talk about is equipotential lines around charges. And we did talk about equipotential lines in the last video. However, in order to understand it a little bit better, let's take a look at contour lines on a map. Equipotential lines are similar to contour lines on a map that trace the altitudes that are the same altitude. Looking at the diagram below, we would know that the line marked 10, right here, is 10 meters above the sea level. When we draw this onto a flat surface, this is what we notice. The more distance there is between the lines, the less altitude gain there is. If you notice this area that has a large distance between the 10-meter line right here and the next line, this is a very flat area that would require a low level of energy to walk because the area is fairly flat. Now, the closer that the lines are, the steeper the ground is. If you notice, the 20-meter line is extremely close to the 30-meter line right here. The line's closeness tells us this is a steeper part of the terrain. This would also correlate to how much work would be needed to hike or climb along these contour lines. As you hike further up in altitude, the more work will be needed because the ground will become more steep. Equipotential lines are similar to contour lines on a map. However, when discussing electric fields, they represent equal potential, or the voltage that is at a particular point. With the contour lines, it's about the same altitude. Equipotential lines are dotted lines that connect equal electric potentials or voltage. If you look at the diagram over here of the two charged plates, there are actually no dotted lines right here. However, the dotted lines would be these green lines that have a certain voltage that is already marked up at the top. And what that states is along this line, the voltage is the same. Now, these lines might remind you of wave fronts that are connecting all the crests of waves from our wave unit, except that these lines connect electric potentials of the same voltage. Equipotentials are not always as evenly spaced and can change shapes depending on nearby charges which have their own fields. One other thing to note is that because voltage is the same along the line, movement along these equipotential surfaces requires no work, so there is no work to move along equipotential surfaces. For example, if you were to place a positive charge, a positive test charge at the 0 equipotential, which is over here, there would be no work required to move anywhere along this line. A third factor to take into account when we're talking about equipotential lines is that the equipotential is always perpendicular to the electric field. Remember, here are the field lines, and the field lines are red and they are directed inwards towards the electron, and the dotted lines are the equipotential lines and they are denoted by various potential differences. The space around the positive charge is labeled with positive equipotential values and the field lines are directed outwards. The values are based off of the equipotential needed to place a positive test charge at that point within the electric field. Notice how the equipotential dotted lines are always perpendicular, or they should be perpendicular, to that of the electric field. If we looked again at the charged plates over here, if we were to take a positively charged particle, a test charge, and place it here, there would be no need for an electric potential, so therefore we have 0 volts because they're attracted to each other. As we move the positive test charge closer to the positively charged plate, then we would need more electric potential to be present in order for that test charge to get closer. Here are 5 practice problems for you to do, and some of them do have multiple parts. This is number 1 and 2, 3, 4, and 5. All right, so we have gotten to the end of our TNOTES. Be ready to use this information in class, and we'll see you soon.